A microcontroller is a small computer on a single integrated circuit containing a processor core, memory, and programmable input-output peripherals. Program memory in the form of NOR flash or OTP ROM is also often included on chip, as well as a typically small amount of RAM. Microcontrollers are designed for embedded applications, in contrast to the microprocessors used in personal computers or other general-purpose applications. Microcontrollers are used in automatically controlled products and devices, such as automobile engine control systems, implantable medical devices, remote controls, office machines, appliances, power tools, toys and other embedded systems. By reducing the size and cost compared to a design that uses a separate microprocessor, memory, and input-output devices, microcontrollers make it economical to digitally control even more devices and processes. Mixed-signal microcontrollers are common, integrating analog components needed to control non-digital electronic systems. Some microcontrollers may use 4-bit words and operate at clock rate frequencies as low as 4 kHz, for low power consumption. They will generally have the ability to retain functionality while waiting for an event such as a button press or other interrupt. Power consumption while sleeping may be just nanowatts, making many of them well suited for long-lasting battery applications. Other microcontrollers may serve performance-critical roles, where they may need to act more like a digital signal processor, with higher clock speeds and power consumption. History: the first microprocessor was the 4-bit Intel 4004 released in 1971. With the Intel 8008 and other more capable microprocessors becoming available over the next several years. However, both processors required external chips to implement a working system, raising total system cost, and making it impossible to economically computerize appliances. The Smithsonian Institution says TI engineers Gary Boone and Michael Cochran succeeded in creating the first microcontroller in 1971. The result of their work was the TMS-1000, which became commercially available in 1974. It combined read-only memory, read-write memory, processor and clock on one chip and was targeted at embedded systems. Partly in response to the existence of the single-chip TMS-1000, Intel developed a computer system on a chip optimized for control applications, the Intel 8048, with commercial parts first shipping in 1977. It combined RAM and ROM on the same chip. This chip would find its way into over 1 billion PC keyboards, and other numerous applications. At that time Intel's president, Luke J. Valenta, stated that the microcontroller was one of the most successful in the company's history, and expanded the division's budget over 25%. Most microcontrollers at this time had two variants. One had an erasable EEPROM program memory, with a transparent quartz window in the lid of the package to allow it to be erased by exposure to ultraviolet light. The other was a PROM variant which was only programmable once. Sometimes this was signified with the designation OTP, standing for one-time programmable. The PROM was actually exactly the same type of memory as the EEPROM, but because there was no way to expose it to ultraviolet light, it could not be erased. The erasable versions required ceramic packages with quartz windows, making them significantly more expensive than the OTP versions, which could be made in lower-cost opaque plastic packages. For the erasable variants, quartz was required, instead of less expensive glass, for its transparency to ultraviolet. Glass is largely opaque to UV, but the main cost differentiator was the ceramic package itself. In 1993, the introduction of Eeprom Memory allowed microcontrollers to be electrically erased quickly without an expensive packages required for EEPROM, allowing both rapid prototyping and in-system programming. The same year, Atmel introduced the first microcontroller using flash memory, a special type of Eeprom. Other companies rapidly followed suit, with both memory types. Cost has plummeted over time, with the cheapest 8-bit microcontrollers being available for under 25 cents in quantity in 2009, and some 32-bit microcontrollers around $1 for similar quantities. Nowadays microcontrollers are cheap and readily available for hobbyists, with large online communities around certain processors. In the future, MRAM could potentially be used in microcontrollers as it has infinite endurance and its incremental semiconductor wafer process cost is relatively low. Volumes: about 55% of all CPUs sold in the world are 8-bit microcontrollers and microprocessors. Over 2 billion 8-bit microcontrollers were sold in 1997, and according to Semico, over 4 billion 8-bit microcontrollers were sold in 2006. More recently, Semico has claimed the MCU market grew 36.5% in 2010 and 12% in 2011. A typical home in a developed country is likely to have only 4 general-purpose microprocessors but around 3 dozen microcontrollers. A typical mid-range automobile has as many as 30 or more microcontrollers. They can also be found in many electrical devices such as washing machines, microwave ovens, and telephones. Embedded design: a microcontroller can be considered a self-contained system with a processor, memory and peripherals and can be used as an embedded system. The majority of microcontrollers in use today are embedded in other machinery, such as automobiles, telephones, appliances, and peripherals for computer systems. While some embedded systems are very sophisticated, many have minimal requirements for memory and program length, with no operating system, and low software complexity. Typical input and output devices include switches, relays, solenoids, LEDs, small or custom LCD displays, radio frequency devices, and sensors for data such as temperature, humidity, light level etc. Embedded systems usually have no keyboard, screen, disks, printers, or other recognizable I/O devices of a personal computer, and may lack human interaction devices of any kind. Interrupts: microcontrollers must provide real-time response to events in the embedded system they are controlling. When certain events occur, an interrupt system can signal the processor to suspend processing the current instruction sequence and to begin an interrupt service routine. The ISR will perform any processing required based on the source of the interrupt, before returning to the original instruction sequence. Possible interrupt sources are device-dependent, and often include events such as an internal timer overflow, completing an analog-to-digital conversion, a logic level change on an input such as from a button being pressed, and data received on a communication link. Where power consumption is important as in battery-operated devices, interrupts may also wake a microcontroller from a low-power sleep state where the processor is halted until required to do something by a peripheral event. Programs: typically microcontroller programs must fit in the available on-chip program memory, since it would be costly to provide a system with external, expandable, memory. Compilers and assemblers are used to convert high-level language and assembler language codes into a compact machine code for storage in the microcontroller's memory. Depending on the device, the program memory may be permanent, read-only memory that can only be programmed at the factory, or program memory that may be field-alterable flash or erasable read-only memory. Manufacturers have often produced special versions of their microcontrollers in order to help the hardware and software development of the target system. Originally these included EEPROM versions that have a window on the top of the device through which program memory can be erased by ultraviolet light, ready for reprogramming after a programming and test cycle. Since 1998, EEPROM versions are rare and have been replaced by Eeprom and Flash, which are easier to use and cheaper to manufacture. Other versions may be available where the ROM is accessed as an external device rather than as internal memory, however these are becoming increasingly rare due to the widespread availability of cheap microcontroller programmers. The use of field programmable devices on a microcontroller may allow field update of the firmware or permit late factory revisions to products that have been assembled but not yet shipped. Programmable memory also reduces the lead time required for deployment of a new product. Where hundreds of thousands of identical devices are required, using parts programmed at the time of manufacture can be an economical option. These mask-programmed parts have the program laid down in the same way as the logic of a chip, at the same time. A customizable microcontroller incorporates a block of digital logic that can be personalized in order to provide additional processing capability. peripherals and interfaces that are adapted to the requirements of the application. For example, the 1891 CAP from Atmel has a block of logic that can be customized during manufacture according to user requirements. Other microcontroller features. Microcontrollers usually contain from several to dozens of general-purpose input-output pins. GPIO pins are software configurable to either an input or an output state. When GPIO pins are configured to an input state, they are often used to read sensors or external signals. Configured to the output state, GPIO pins can drive external devices such as LEDs or motors. Many embedded systems need to read sensors that produce analog signals. This is the purpose of the analog-to-digital converter. Since processors are built to interpret and process digital data, that is ones and zeros, they are not able to do anything with the analog signals that may be sent to it by a device. So the analog-to-digital converter is used to convert the incoming data into a form that the processor can recognize. A less common feature on some microcontrollers is a digital-to-analog converter that allows the processor to output analog signals or voltage levels. In addition to the converters, many embedded microprocessors include a variety of timers as well. One of the most common types of timers is the programmable interval timer. A PIT may either count down from some value to 0, or up to the capacity of the count register, overflowing to 0. Once it reaches 0, it sends an interrupt to the processor indicating that it has finished counting. This is useful for devices such as thermostats, which periodically test the temperature around them to see if they need to turn the air conditioner on, the heater on, etc. A dedicated pulse width modulation block makes it possible for the CPU to control power converters, resistive loads, motors, etc. without using lots of CPU resources in tight timer loops. Universal asynchronous receiver transmitter block makes it possible to receive and transmit data over a serial line with very little load on the CPU. Dedicated on-chip hardware also often includes capabilities to communicate with other devices in digital format such as ES2C and serial peripheral interface. Higher integration. Microcontrollers may not implement an external address or data bus as they integrate RAM and non-volatile memory on the same chip as the CPU. Using fewer pins, the chip can be placed in a much smaller, cheaper package. Integrating the memory and other peripherals on a single chip and testing them as a unit increases the cost of the chip, but often results in decreased net cost of the embedded system as a whole. Even if the cost of a CPU that has integrated peripherals is slightly more than the cost of a CPU and external peripherals, having fewer chips typically allows a smaller and cheaper circuit board, and reduces the labor required to assemble and test the circuit board, in addition to tending to decrease the defect rate for the finished assembly. A microcontroller is a single integrated circuit, commonly with the following features: central processing unit, ranging from small and simple 4-bit processors to complex 32 or 64-bit processors, volatile memory for data storage, ROM, Eeprom or flash memory for program and operating parameter storage, discrete input and output bits, allowing control or detection of the logic state of an individual package pin, serial input-output such as serial ports, other serial communications interfaces like ES2C, serial peripheral interface and controller area network for system interconnect, peripherals such as timers, event counters, PWM generators, and watchdog, clock generator, often an oscillator for a quartz timing crystal, resonator or RC circuit. Many include analog to digital converters, some include digital to analog converters. In circuit programming and debugging support, this integration drastically reduces the number of chips and the amount of wiring and circuit board space that would be needed to produce equivalent systems using separate chips. Furthermore, on low pin count devices in particular, each pin may interface to several internal peripherals, with the pin function selected by software. This allows a part to be used in a wider variety of applications than if pins had dedicated functions. Microcontrollers have proved to be highly popular in embedded systems since their introduction in the 1970s. Some microcontrollers use a Harvard architecture, separate memory buses for instructions and data, allowing accesses to take place concurrently. Where a Harvard architecture is used, instruction words for the processor may be a different bit size than the length of internal memory and registers. For example, 12-bit instructions used with 8-bit data registers. The decision of which peripheral to integrate is often difficult. The microcontroller vendors often trade operating frequencies and system design flexibility against time-to-market requirements from their customers and overall lower system cost. Manufacturers have to balance the need to minimize the chip size against additional functionality. Microcontroller architectures vary widely. Some designs include general-purpose microprocessor cores, with one or more ROM, RAM, or I/O functions integrated onto the package. Other designs are purpose-built for control applications. A microcontroller instruction set usually has many instructions intended for bitwise operations to make control programs more compact. For example, a general-purpose processor might require several instructions to test a bit in a register and branch if the bit is set, where a microcontroller could have a single instruction to provide that commonly required function. Microcontrollers typically do not have a math coprocessor, so floating-point arithmetic is performed by software. Programming environments, microcontrollers were originally programmed only in assembly language, but various high-level programming languages are now also in common use to target microcontrollers. These languages are either designed specially for the purpose, or versions of general-purpose languages such as the C programming language. Compilers for general-purpose languages will typically have some restrictions as well as enhancements to better support the unique characteristics of microcontrollers. Some microcontrollers have environments to aid developing certain types of applications. Microcontroller vendors often make tools freely available to make it easier to adopt their hardware. Many microcontrollers are so quirky that they effectively require their own non-standard dialects of C, such as SDCC for the 8051, which prevent using standard tools even for code unrelated to hardware features. Interpreters are often used to hide such low-level quirks. Interpreter firmware is also available for some microcontrollers. For example, BASIC on the early microcontrollers Intel 8052. BASIC and Forth on the Zilog Z8 as well as some modern devices. Typically these interpreters support interactive programming. Simulators are available for some microcontrollers. These allow a developer to analyze what the behavior of the microcontroller and their program should be if they were using the actual part. A simulator will show the internal processor state and also that of the outputs, as well as allowing input signals to be generated. While on the one hand most simulators will be limited from being unable to simulate much other hardware in the system, they can exercise conditions that may otherwise be hard to reproduce at will in the physical implementation, and can be the quickest way to debug and analyze problems. Recent microcontrollers are often integrated with on-chip debug circuitry that when accessed by an in-circuit emulator via JTAG, allow debugging of the firmware with a debugger. Types of microcontrollers. As of 2008 there are several dozen microcontroller architectures and vendors including ARM core processors. ARM Cortex-M cores are specifically targeted towards microcontroller applications. Atmel AVR, AVR32, and 1891 SAM, Cypress Semiconductors M8C core used in their PSoC, Freescale Coldfire and SO8, Freescale 68HC11, Intel 8051, Infineon, 8-bit XC800, 16-bit XE166, 32-bit XMC4000, 32-bit TRI core and 32-bit Oryx tri-core-bit microcontrollers, MIPS, Microchip Technology PIC, NXP Semiconductors LPC1000, LPC2000, LPC3000, LPC4000, LPC900, LPC700, Parallax Propeller, PowerPC-ISE, Rabbit 2000, Renesas Electronics. RL78 16-bit MCU. RX 32-bit MCU. Super H. V850 32-bit MCU. H8. R8C 16-bit MCU, Silicon Laboratories pipelined 8-bit 8051 microcontrollers and mixed-signal ARM-based 32-bit microcontrollers, STMicroelectronics STM8, ST10 and STM32, Texas Instruments TIMSP430C2000, Toshiba TLCS870. Many others exist, some of which are used in very narrow range of applications or are more like applications processors than microcontrollers. The microcontroller market is extremely fragmented, with numerous vendors, technologies, and markets. Note that many vendors sell or have sold multiple architectures. Interrupt latency. In contrast to general-purpose computers, microcontrollers used in embedded systems often seek to optimize interrupt latency over instruction throughput. Issues include both reducing the latency and making it be more predictable. When an electronic device causes an interrupt, the intermediate results have to be saved before the software responsible for handling the interrupt can run. They must also be restored after that software is finished. If there are more registers, this saving and restoring process takes more time, increasing the latency. Ways to reduce such context restore latency include having relatively few registers in their central processing units, or at least having the hardware not save them all. Another technique involves spending silicon gates on shadow registers, one or more duplicate registers used only by the interrupt software, perhaps supporting a dedicated stack. Other factors affecting interrupt latency include cycles needed to complete current CPU activities. To minimize those costs, microcontrollers tend to have short pipelines, small write buffers, and ensure that longer instructions are continuable or restartable. Reduced instruction set computing risk design principles ensure that most instructions take the same number of cycles, helping avoid the need for most such continuation restart logic. The length of any critical section that needs to be interrupted. Entry to a critical section restricts concurrent data structure access. When a data structure must be accessed by an interrupt handler, the critical section must block that interrupt. Accordingly, interrupt latency is increased by however long that interrupt is blocked. When there are hard external constraints on system latency, developers often need tools to measure interrupt latencies and track down which critical sections cause slowdowns. One common technique just blocks all interrupts for the duration of the critical section. This is easy to implement, but sometimes critical sections get uncomfortably long. A more complex technique just blocks the interrupts that may trigger access to the data structure. This is often based on interrupt priorities, which tend to not correspond well to the relevant system data structures. Accordingly, this technique is used mostly in very constrained environments. Processors may have hardware support for some critical sections. Examples include supporting atomic access to bits or bytes within a word, or other atomic access primitives like the load link LDREX/STREX exclusive access primitives introduced in the ARMv6 architecture. Interrupt nesting. Some microcontrollers allow higher priority interrupts to interrupt lower priority ones. This allows software to manage latency by giving time-critical interrupts higher priority than less critical ones. Trigger rate. When interrupts occur back-to-back, microcontrollers may avoid an extra context save restore cycle by a form of tail call optimization. Lower-end microcontrollers tend to support fewer interrupt latency controls than higher-end ones. Microcontroller embedded memory technology. Since the emergence of microcontrollers, many different memory technologies have been used. Almost all microcontrollers have at least two different kinds of memory, a non-volatile memory for storing firmware and a read-write memory for temporary data. From the earliest microcontrollers to today, 6-transistor SRAM is almost always used as the read-write working memory, with a few more transistors per bit used in the register file. FRAM or MRAM could potentially replace it as it is 4 to 10 times denser, which would make it more cost-effective. In addition to the SRAM, some microcontrollers also have internal Eeprom for data storage. And even ones that do not have any are often connected to external serial Eeprom chip or external serial flash memory chip. A few recent microcontrollers beginning in 2003 have self-programmable flash memory. Firmware. The earliest microcontrollers used mask ROM to store firmware. Later microcontrollers had quartz windows that allowed ultraviolet light in to erase the EPROM. The microchip PIC16C84, introduced in 1993, was the first microcontroller to use Eeprom to store firmware. In the same year, Atmel introduced the first microcontroller using NOR flash memory to store firmware. See also: List of common microcontrollers, microbotics, programmable logic controller, single board microcontroller, PIC microcontroller. References. External links: How to program a microcontroller, Microcontroller at DMOZ, Embedded Systems Design Magazine.